Picture the most extraordinary animal migration ever recorded. Emperor penguins traveling not just across Antarctic ice, but through the vacuum of space itself. Their sleek bodies perfectly adapted to survive where no Earth creature should be able to exist. What if evolution had taken the remarkable cold weather adaptations that already make penguins masters of Earth's most hostile environments and pushed them to their ultimate extreme, creating the first truly spacefaring vertebrates in our planet's history? The story begins with understanding just how remarkable penguins already are in conquering extreme conditions that would kill most other animals. Emperor penguins routinely survive Antarctic temperatures that plummet to -70 degrees Celsius, conditions cold enough to freeze gasoline solid within minutes. Their bodies represent 400 million years of evolutionary refinement, equipped with multiple layers of scale-like feathers that create such efficient insulation that very strong winds exceeding 60 kilometers per hour are required to penetrate their thermal barrier. Even more impressive, these birds possess a sophisticated counter-current heat exchange system in their circulatory system, where warm arterial blood flowing to their extremities transfers heat to the cold venous blood returning to their core, preventing dangerous heat loss while maintaining circulation to their feet and flippers, even in sub-zero conditions. The diving abilities of emperor penguins reveal physiological adaptations that already begin to approach the extreme oxygen management required for space survival. These remarkable birds can hold their breath for over 27 minutes while diving to depths exceeding 500 meters, managing their oxygen stores with precision that surpasses even the most advanced human breath-holding techniques. Their respiratory system, comprising specialized air sacs and lungs, constitutes up to 50% of their total body oxygen reserves, and they possess the extraordinary ability to maintain arterial hemoglobin saturation above 90% for most of even their longest dives. Perhaps most remarkably, emperor penguins can tolerate blood oxygen levels that would cause immediate unconsciousness in humans, demonstrating a fundamental adaptation to extreme hypoxic conditions that represents the first step toward space-worthy physiology. The molecular biology underlying these adaptations provides crucial insights into how evolution might theoretically push penguin physiology even further toward space compatibility. Emperor penguins carry specialized genes like DSG1 that help them maintain skin integrity in extreme cold, while their myoglobin proteins have evolved unique structures that allow efficient oxygen storage and transport in muscle tissue under low oxygen conditions. These adaptations represent the foundation upon which space evolution could theoretically build, using the same evolutionary mechanisms that already allow penguins to thrive in environments that challenge the limits of vertebrate survival. To understand how penguins might evolve for space survival, we must first examine the organisms that have already achieved this seemingly impossible feat. Tardigrades, microscopic animals no larger than a grain of sand, have demonstrated that Earth life can indeed survive the vacuum of space, extreme radiation, and temperature swings from near absolute zero to over 150 degrees Celsius. In 2007, these remarkable creatures became the first animals to survive direct exposure to the space environment aboard the European Space Agency's Photon M3 mission, spending 12 days in the vacuum of space and returning alive. Their secret lies in a process called cryptobiosis, where they essentially shut down all metabolic processes, lose 99% of their body water, and enter a death-like state that can persist for decades before revival when favorable conditions return. The evolutionary pathway from Antarctic penguin to space-adapted penguin would require millions of generations and environmental pressures that gradually increased in severity. This transformation might begin with populations of penguins that became isolated in increasingly extreme environments, perhaps in high-altitude Antarctic valleys where atmospheric pressure approaches space-like conditions and temperatures remain permanently below those of the current penguin habitat. Over countless generations, natural selection would favor individuals with enhanced versions of existing penguin adaptations, more efficient oxygen storage systems, improved cellular repair mechanisms to handle increased radiation exposure, and modified feather structures that could provide protection in near-vacuum conditions. The first major evolutionary hurdle would be developing the ability to survive in vacuum conditions that cause rapid dehydration and cellular damage. Space-evolved penguins might develop a modified version of the tardigrades' cryptobiosis mechanism, but adapted for a much larger, more complex vertebrate body. Their already sophisticated circulatory system could evolve specialized valves and pressure chambers that would allow them to rapidly enter a hibernation-like state when atmospheric pressure drops, similar to how current penguins already slow their heart rates and redirect blood flow during extreme diving conditions. The thick layer of blubber that currently provides thermal insulation could develop additional functions, serving as a biological pressure suit that maintains internal body pressure during vacuum exposure. Temperature regulation in space presents unique challenges that would require radical modifications to existing penguin thermoregulation systems. In the vacuum of space, heat can only be lost through radiation, not through conduction or convection, as occurs in Earth's atmosphere. Space-adapted penguins might evolve specialized patches of highly vascularized skin that could function as biological radiators, allowing controlled heat dissipation when needed, while their existing countercurrent heat exchange systems could be enhanced to provide even more precise temperature control. Their feathers might evolve metallic properties, incorporating trace elements that could reflect harmful radiation while maintaining insulation properties, similar to how some extremophile organisms already incorporate unusual materials into their cellular structures. The challenge of cosmic radiation would drive perhaps the most dramatic evolutionary adaptations in spacefaring penguins. Current research shows that some microorganisms exposed to space develop enhanced resistance to gamma radiation and other forms of cellular damage. Space penguins might evolve enhanced DNA repair mechanisms, similar to those found in tardigrades, possibly developing specialized cellular organelles dedicated to detecting and repairing radiation damage in real time. Their already unique myoglobin proteins could evolve additional functions, serving not only for oxygen storage, but also as biological radiation shielding within muscle tissue. Oxygen management would represent the ultimate test of penguin evolutionary plasticity in space environments. Building upon their existing diving physiology, space penguins might develop the ability to enter extended periods of suspended animation, similar to how they currently manage oxygen during deep dives, but lasting for months rather than minutes. Their respiratory air sacs could evolve into specialized internal atmosphere chambers, maintaining small pockets of breathable gas under pressure for extended periods. Most remarkably, they might develop the ability to extract and store oxygen from ice or other materials they encounter during space travel, using specialized enzymes similar to those found in extremophile organisms that can break down unusual chemical compounds for energy. Navigation and sensory adaptation for space travel would push penguin neurobiology in entirely new directions. Their existing magnetic navigation abilities, used for finding feeding grounds across vast Antarctic waters, could evolve into sophisticated systems for detecting gravitational fields and electromagnetic signatures of celestial bodies. Their eyes, already adapted for seeing underwater in low light conditions, might develop the ability to perceive different wavelengths of electromagnetic radiation, allowing them to navigate by stellar positions and identify potentially habitable environments from vast distances. The social and reproductive adaptations of space penguins would create entirely new forms of cooperative behavior. Current emperor penguins already demonstrate remarkable social thermoregulation, huddling together in groups of thousands to survive Antarctic blizzards. Space-adapted penguins might evolve the ability to link their biological systems together during long-distance space travel, sharing oxygen reserves and thermal regulation across entire flocks, creating a form of biological spacecraft where individual penguins function as specialized components of a larger living system. Their reproductive cycles could become synchronized with celestial events, timing breeding to coincide with orbital periods, or the discovery of suitable nesting environments on asteroids or planetary surfaces. Perhaps the most fascinating aspect of space penguin evolution would be their potential development of biological space travel capabilities. Rather than simply surviving in space, they might evolve the ability to actively navigate through zero gravity, using modified flipper structures that could function as attitude control systems. Their streamlined body shape, already perfected for efficient movement through water, could prove remarkably well suited for propulsion in vacuum conditions. They might even develop the ability to metabolize unusual materials found in space, such as ice from comets or mineral deposits on asteroids, expanding their potential habitat range throughout the solar system. The ecological implications of space-adapted penguins would be revolutionary for our understanding of life's potential distribution throughout the universe. These hypothetical creatures would represent the first complex vertebrates capable of surviving and potentially thriving in the space environment, opening the possibility for the establishment of self-sustaining populations on multiple worlds. Their ability to travel between planets or asteroids could make them inadvertent vectors for transporting other forms of Earth life throughout the solar system, potentially seeding life on previously sterile worlds. The scientific study of such creatures would provide unprecedented insights into the ultimate limits of biological adaptation and the potential for Earth life to colonize other worlds. Their existence would demonstrate that the gap between Earth life and space life is not insurmountable, but rather represents another step in evolution's endless ability to find solutions to seemingly impossible survival challenges. The molecular mechanisms they evolved for space survival could inspire new technologies for human space exploration, from improved life support systems to novel approaches for long-duration space travel. Yet even as we explore these speculative possibilities, we must acknowledge the immense challenges and limitations that would constrain such evolutionary development. The energy requirements for maintaining complex vertebrate life in space environments would be enormous, and the evolutionary timeframes required for such radical adaptations would likely span millions of years under very specific environmental pressures. The transition from aquatic diving to vacuum survival represents a biological leap that may be too extreme for natural selection to bridge, given the fundamental differences between these environments. The story of space-adapted penguins ultimately serves as a thought experiment that illuminates both the remarkable adaptability of life and the genuine constraints that govern evolutionary possibility. While current penguins already possess many of the foundational adaptations that could, theoretically, be enhanced for space survival, the magnitude of change required would likely exceed what is biologically feasible through natural evolutionary processes. Nevertheless, contemplating such extreme evolutionary scenarios expands our understanding of life's creative potential and challenges us to consider how the remarkable organisms we share our planet with today represent just one chapter in the ongoing story of life's adaptation to an ever-changing universe. What other impossible adaptations might evolution achieve given enough time and the right environmental pressures? And what would those discoveries teach us about the nature of life itself?